Yeah, thank you. So first of all, I would like to thank Stephan for inviting me here and...
Could you speak up, please?
Yeah, inviting me here and allowing to give this talk. And you can see the character on board. And the point is I would like to express ordinary differential cohomology. I will explain what this means in a few minutes maybe, of a smooth manifold X as isomorphism classes of smooth n-dimensional topological field series over X. And of course, I will also explain what that means, but maybe not immediately. So this statement involves a lot of complicated machinery, like infinity n categories, symmetric monoidal structures, everything is fibered over smooth manifolds. So I thought it would be best to explain the easy case first, namely the one-dimensional case, in which you have three flavors of topological field series, which I call discrete, smooth, and homotopy. And as we will see, those correspond in a very precise sense to different types of line bundles over some smooth manifold X, namely flat, line bundles with connection, and just line bundles without any structures. And the second part of the talk will be about generalizing this description of such three types of line bundles to arbitrary dimension. So to say, the goal is to categorize this, and in particular, part B categorizes to something known as differential cohomology, and I will explain what that means maybe in this part. Okay, so maybe it makes sense to start with a little bit of motivation. Why would we expect that this differential cohomology actually arises as isomorphism classes of some topological field series? So the motivation here is a Cobordism hypothesis, which of course is now a theorem due to Hopkins and Lurie. Which, well, I will only use the most easy version, namely those that works with framed manifolds. So the statement is that if, say, X is a space and C is something called infinity n category, so you can think of it as a category that has morphisms at all levels, and morphisms at level greater than n are invertible. And then I also require some condition, namely that all objects and morphisms and so on are generalizable. So, for example, so it's actually a symmetric monoidal infinity n category. So if, for example, you have a monoidal category of vector spaces, then generalizable objects are finite dimensional vector spaces. And if you have such two pieces of data, you can explicitly compute the space of topological field series over X framed. So such field series are symmetric monoidal functors from a certain n category, infinity n category of Cobordisms over X. And I guess most of you are, probably everybody here is familiar with what a field theory is. And you take C as a target category. And this happens to be equivalent to the space of maps from X to the core of C. So this is simply the infinity category which you can obtain from C by discarding non-reversible morphisms. So as an example, one can take n to be equal to 1. And for example, if the target category is a category with one object and morphisms being elements of U1, then you can prove that you actually get flat line bundles.
Excuse me, I didn't get what K of C is.
Yeah, so you take C. This is an infinity n category that can have non-invertible morphisms. You have to discard all of those.
So
and that's
you get a space.
Yeah, then you get a space.
I have a question about that. I was sort of surprised because I thought the right-hand side would be like fully dualizable objects in C. Is that somehow?
Well, I think it has duals, so I mean.
I just mean, is that right-hand side somehow equivalent to? Maybe I should.
No, I just assume from the start that all objects are that this category is fully dualizable. So, I mean, in general, you would put like FD here, but here I just assume it from the start.
I'm not sure if this might address it, but maybe you were thinking of X as a point. I think that's what I was thinking.
Yeah.
Thank you.
Okay, so we have this nice, beautiful statement, but which in particular allows us to explicitly compute parts A and C in this example, but somehow it fails to express part B, and the reason for that is that the notion of connection on a smooth line bundle requires you to know the smooth structure on a manifold, whereas this theorem only uses like the topological space structure. It doesn't have anything to do with a smooth manifold structure. But one could try to make a guess what would happen if somehow we replace this with a certain smooth version, and I will, like most of the talk will be about explaining what does it mean to make the source smooth. Like somehow, if you have a family of K morphisms which varies smoothly over some smooth manifold, then the condition is that the value in this target should also vary smoothly. But okay, that's very imprecise, but I will try to explain this in more detail a little bit later. So, so the statement, which I have to put in quotes because it's completely non-rigorous, and like I don't even know how to define all objects that I will use in the statement, but which nonetheless helps to develop intuition of what's going on, is as follows. So, conjecture: if X is a smooth manifold, and C is the same as before, but now fibered over smooth manifolds. So this essentially formalizes what do I mean by a smooth functor. Then we would like to have some statement of the form symmetric monadical functors from some smooth version of Cobordism and category, which I will say, well, let's put the word smooth here, over X to C should be well, again, let's put quotes here because it's not rigorously defined, but the idea is that here you have some kind of what is like playing out of this space. Well, to every point of X, you assign some object in this category. Well, the idea is that you should now have a smooth bundle of objects, and furthermore, it should have some notion of connection. So, differential refinement of maps smooth to from X to KC. Of course, as I said, that's very imprecise. For example, I cannot really define this object for you, but
is the left-hand side have a definition?
The question is, does the left-hand side have a definition? And the answer is yes. We can formalize the left-hand side. And I will do in some easy examples a little bit later.
How should I mean, the objects of board N are smooth already, right? So what does it mean to put smooth?
Well, it simply means that, so the question is, what does it mean to put smooth here?
No, on the, I'm sorry, on the left side, above board N frame.
Oh, here? You mean this smooth?
Yeah.
So the question is, what does this smooth mean here? And it simply refers to this statement that everything is fibered over manifolds. So in particular, if you have a smooth family of K-morphisms here, the requirement is that in this triangle, you also get a smooth family. And yeah, we will see examples later, maybe. So the point is, even though we don't know what this differential refinement is, we can say what it should be in some very easy cases, like, for example, differential refinement of line bundles should be line bundles with connection. And more generally, differential refinements of categorification of line bundles, which are sometimes called bundle n-gerbs, should be bundle n-gerbs with connection. So that's what the second part is supposed to be about. Okay, I guess that's enough for motivation. So let's try to develop more or less rigorously some simple examples that serve to illustrate this thesis about differential refinements. So before I describe a differential refined version, which is in part B, I would like to say a few words about the familiar case, which does not involve like any of this smooth business, which is simply the usual a T-Siegel style topological field series. So part 1a is about discrete one-dimensional TFTs. So let's start with a definition. Let's say you have a X is a space. Then a one-dimensional TFT over X, and I guess I should say from the start that my target will be very restricted. Like here you could have arbitrary target, but my target will be always very, very simple and category. It will have just one morphism at every level, except one level at which it has some abelian group. So the character will always be something like Bn of some abelian group. So in our case, we so is a functor from the category of from the fundamental groupoid of X to something I call B U1 with discrete topology. So let's explain, well, I guess I shouldn't really explain what fundamental groupoid is, but objects are points of X, and morphisms are homotopic classes of paths between points. This category has only one object, and morphisms are precisely the set of elements with U1, and the word discrete here means that I don't put any topology on U1. So those of you who are more experienced in like in the language, sorry? Why do I have what, sorry? B is because, I mean, U1 lives at the level of one morphisms. Without B, I would just put U1 at the level of objects.
I mean, B usually means classifying space.
It is a classifying space. Yeah, B can be tropic. I mean, this is a category whose morphisms are invertible. So that's infinity groupoid. Infinity groupoid is a space, so that's a classifying space. So those of you who are more familiar with topological field theories see at least probably two problems with this definition. Well, as you might guess, I intend to claim that isomorphism classes of such one-dimensional TFTs are flat line bundles. And of course, with this definition, it cannot really be true because the target somehow is not rich enough. You would expect something like line bundles here instead of just this trivial category. So the point is that I will make a simplifying assumption throughout the talk, which is justified by the fact, so maybe remark. So all categories, all functors and so on, so everything is a stack with respect to X. With respect to X. So we can assume that X is diffeomorphic to Rn. So what I claim is that using the machinery of stacks and disaggregator, you can get like the statement for arbitrary X, because arbitrary smooth manifold can be covered by something which is diffeomorphic to Rn. So you don't really lose any generality here, like, but things become much more easy to describe. Like this category is more easy to describe than line bundles, for example.
But still, you get naively flat line bundles if you write out there, so you don't need to go to stacks.
Yes, but somehow I would like to keep the language consistent throughout the talk. So,
I mean, a map from X to BU1, that just seems like just a line bundle, not a flat line.
No, it's I will yeah, I will explain this point in a second. So, well, the claim is now that proposition maybe. So, one-dimensional TFTs over X, I should add the word discrete here, of course, form a groupoid whose morphisms are natural transformations between such functors. So in particular, you can talk about isomorphism classes of that groupoid.
Is it easy to say why does this discreteness mean that the bundle is flat?
I'm saying exactly this right now.
Okay.
So let's put it this way. So isomorphism classes of one-dimensional TFTs over X are the same as isomorphism classes of flat line bundles over X. So why is this true actually? Well, let's define a map this way. So you start with a flat line bundle over X. And the way you produce a one-dimensional TFT is, well, so objects in the Cobordism category are points in X. And, well, you have to send all of those to the only object in the target. So there is not much choice here. What about morphisms? If you have a homotopic class of paths between 2 points, you can of course use a parallel transport over such a path. Well, strictly speaking, we don't have a chosen path. We only have a homotopic class of such paths, but because the line bundle is flat, the parallel transport map is invariant under homotopy, so you do get an honest functor on this category. So that's where flat condition is important. And that's where discreteness of U1 is also important. And of course, the set is also equal to first cohomology of X with U1 discrete. And this is, of course, true for arbitrary X, not just for X, which is diffeomorphic to Rn. OK. Any questions so far? So let's end part A here, and let's move on to the more interesting case. Namely, I would like to explain how you can remove this flatness restriction on line bundles and just get arbitrary line bundles with connection. So you would expect that the definition should be pretty similar. If you have an arbitrary line bundle, you can still get some sort of one-dimensional TFT over X. Namely, you send a point to this only object, and a smooth path between 2 points, you can map to parallel transport. So how can we make this precise so that this theorem is now true? So I should say discrete here, by the way. It's true if we replace discrete with smooth and flat with just line bundles with connection. So this is in fact a well-known result. I guess the earliest reference I know is due to Jan Fried, so in 1992, I guess. So all what happens is on this blackboard should be attributed to Jan Fried. So let's follow the same strategy as here. First, we define what a smooth one-dimensional TFT over X is. So if X is a manifold, then one-dimensional TFT over X smooth. Is a functor between what categories. So let me write down first notation for those categories, and then I will explain how those are defined. Well, the source is a smooth category of one-dimensional Cobordisms over X. And the target is a smooth version of this category. So what kind of objects are those? Those are not ordinary categories. Like here, everything is just an ordinary category, like very familiar language. But because of this smoothness condition, we have to do something much more complicated. Namely, we have to use the language of Grothendieck fibrations. So everything is now fibered over smooth manifolds. So I will not try to give a very precise description of what a Grothendieck fibration is. Instead, I will just illustrate it in this particular case what it actually means. So this category, let's describe one-dimensional Cobordism category over X. So the gauge, what does it mean to specify such a fibered category? It means that for every smooth manifold S, so for every smooth manifold S, we have the category of one Cobordisms over X fibered over S. So that's an ordinary category. And if you have a map between two manifolds, say from S to T, then we have a functor, which we call a pullback functor. So we have a pullback functor. Pullback functor. From the category of smooth Cobordisms over T to S. So that's the general structure of fibered category. And let's now describe what those categories actually are.
So this
Yep.
is like a functor from manifolds to the category?
Yes, yes. So essentially this amounts to saying that you have a functor from man up to categories. Well, this requires some clarification. Strictly speaking, this is a bicategory, where this is just an ordinary category, so you have to use the appropriate notion of functor, but let's suppress this technical detail here. So let's describe what those categories and functors actually are. So this category has its objects are, well, the way you should think about it is that over this manifold S, over each point of this manifold S, you have something which looks like this. So I can call this board 1 Borg over X discrete. So over each point of S, you have some object and with a map to X, and similarly for morphisms. So let's make this more precise. So objects are simply maps from S to X, smooth map. So the way you think about it is over every point of S, you have a choice of an object like here. So an object here is a map from a point to X. So over every point of S, you have a map from a point to X, or in other words, a point in X. So you have a smooth map from S to X. Is it clear enough, or maybe I should explain it like in a different way? Or okay. And similarly, morphisms are slightly more difficult to describe, but not that difficult. So a morphism between, say, so let's choose two objects, say S and T. A morphism between such two objects is two maps from S to X. Those are objects. So F, G are objects. We would like to say what is a morphism from F to G. Well, such a morphism is the following data. So you have a bundle over S with fibers being intervals. So I should maybe denote it like this. So this is a typical fiber of this P. And furthermore, you have a map from E to X such that, well, you see like E, at every point of S, the fiber looks like an interval. This means that the boundary of E can be decomposed as, well, what is the boundary of E? It's S times the boundary of an interval. So you can think of it as a disjoint union of two copies of S.
I mean, maybe it's confusing. I mean, couldn't you allow for objects, say, coverings? I mean, a map from a covering of S to X?
Well, as I said, like we can assume that. Yeah, I guess.
Because you want to have more than one point.
Okay, yeah, a second remark here. Yeah, that's a very good question. So the question is, you would expect the cobordism category has zero-dimensional manifolds as objects, not just points, but all compact zero-dimensional manifolds. But to simplify things a little bit, I will systematically suppress everything related to a monoidal structure. So that's why in particular I define it here as just the fundamental groupoid of X, even though usually you would expect something slightly more complicated, namely like objects should be like finite disjoint union of points, and morphisms should be one-dimensional Cobordisms, but like everything related to monoidal structures is suppressed. For simplicity. Yeah, so with this remark in mind, now it should be more clear why I have such objects and such morphisms. So the boundary of this bundle can be decomposed as two maps, as two copies of S, and those, by restricting this map, has a map to X. And we specify which part of the boundary is incoming and which part is outgoing. So that's part of the data of morphism is a description of which part is incoming and which part is outgoing. And then this map has to be equal to F disjoint union G. So that's this map. So that's restriction of, say, this map Q to the boundary of E. So
there must be some orientability condition. What if S is the circle, E is the Mobius band?
Sorry, say again?
What if S is the circle and E is the Mobius band with boundary? The boundary of that is one circle, not two copies of a circle.
Yeah, so I only consider like such, only consider when the boundary can be decomposed. So yeah, the question is like, it is theoretically possible that S is the circle and E looks like Möbius bundle. But in this condition, this is actually a requirement that DE is decomposed in such a way which excludes this example.
But I mean, it's still confusing because, I mean, you want to, at the end, you want to calculate the maps, yeah? You want to have this equality. Yeah? But if you forget the tensor on the left-hand side, I mean, then
yeah, I mean,
to get
we do have a tensor in the full version, but
yeah, but I mean, you see, if you don't take the parameterized version, then I mean, somehow because your category, I mean, the tensor category is somehow freely generated by points. I mean, you can forget the tensor and just take 1 point, everything then comes out.
yeah.
Now, in the parameterized case, I mean, it's not free in the.
It is free in the appropriate sense. So the question is like, in the non-fiber case, we can forget about objects being several points. We can just restrict to the simple category because, in a certain sense, this category is free monoidal. The full category of Cobordisms is, in a certain sense, free monoidal category on this smaller category. And I claim the same statement is true, appropriately formulated in the fiber case. So again, in the appropriate sense, the full category of one-dimensional Cobordisms is a free symmetric monoidal smooth category on this restricted category. So the question is, how do we compose such maps? That's a very good question. So here again, I suppressed some small detail. Namely, if you try to compose such maps on the nodes, you will encounter a problem. Namely, that if you have two paths, and if you try to compose them in the obvious way, then the composition doesn't seem to be smooth. Because at the point where target and source meet, you can have an angle. But so this can be resolved in two ways. For example, one can simply allow piecewise smooth morphisms. Or a more elegant approach is to require that points on the boundary of interval have small germs. So they have a small neighborhood which extends this interval a little bit past this point, here and here. And then when you try to glue things, those little neighborhoods have to agree when you do composition. So now this is little neighborhood is also part of the object. So an object now is not just a point, but a small germ of one manifold around this point. And when you compose things, you require that, say you have another morphism here. You require that those little germs agree, which allows you to proves that the composition is always a smooth interval. But again, this is, yeah. Yeah, that's also another, so another way to resolve the problem is to require intervals to be as maps from 0, 1 to x. You can require this map to be constant near endpoints, and yeah, that's another way to resolve the problem with composition. But again, this is all pretty much irrelevant for what I'm trying to describe, so I would rather stick to the simple version. Maybe it's a little bit naive and not precisely true, but it can be made precise if only we had more time. Okay. So, any other questions about the definition of this category before we move on? So maybe the remaining piece is to describe those functors, pullback functors. But that's pretty easy. Like, it's, well, if we have a map from S to T, then a functor between such categories well, that's simply the usual pullback along the map, say, F. So there is nothing special about those functors. So maybe one way to interpret informally is the statement is that what this amounts to saying is that in this setting you could, like in the setting of discrete category, you could say that, well, objects are maps from points to x, a map from a point to x. But now you no longer think about this set of objects as a set. You now think about it as a manifold. So one way to think about this approach informally is to say that the objects now form a smooth manifold, and morphisms also form a smooth manifold. And when you talk about functors, a functor is a map on objects and a map on morphisms. Those two maps have also have to be smooth maps. So, for example, on the level of objects, once you consider this space of objects as a smooth manifold, which is simply X, then a Freiberg functor would send X to the space of objects here, which is trivial, so that's not much, but it would also send the space of morphisms, which is the space of smooth paths in X, to U1, which we will now equip with the smooth topology. And that is, of course, very different from a map from this path space to the discrete space. So you can already see that this definition gives us very different answer for this problem. Okay, I guess I have to erase something. So we are done with this, we are here.
Could you say what you're trying to do is to describe categorical language the conditions on the holonomy thought of as a functor so that they will be given by a smooth connection on a line bundle?
Yeah, exactly. So the question is like, well, it's not a question maybe, but the point is that the point of those smooth functors is that, yes, we want to describe holonomy of line bundles with connections as some kind of smooth map from maybe the space of loops in X to U1. Yeah. Okay, so once we have this definition, and strictly speaking, I also have to define what the target category is. So what is this VU1 smooth? Well, it's pretty easy to describe. So VU1 smooth is, well, again, if you fix this a smooth manifold S, then there is only one object. So just one object. Yeah, so we are describing here the category VU1 smooth of S. Object, there is just one object, and morphisms are smooth maps from S to U1. And I guess you can figure out the pullback functors yourselves. That's an exercise. Now, once we define those two fiber categories, we can say that a one-dimensional. So we can say that a functor between such fiber categories, in our case, a functor between smooth one-dimensional Cobordisms over X to BU1. Well, it is what you expect it to be. We know that the source and the target can be thought of as functors from man-op to categories. So a functor between such categories is a natural transformation between such functors. So natural transformation in the appropriate categorical, higher categorical sense, of course, between functors from man-op to cat. So if you expand this definition, it means that for every smooth manifold S, and for every object in this category fibered over S, so for every smooth map from S to X, you should get an object in the target category over S, which is in this case just a point, so in this case it happens to be trivial. But for morphisms, you do get something non-trivial. So for every manifold S, and for every morphism in the category of one-dimensional Cobordisms over S, for every such morphism, which looks like a bundle of intervals over S, you get a morphism in the target category, which is a smooth map from S to U1 with its smooth structure, of course. So what it means that you intuitively think about the value of this morphism. So you have a family of paths, and you think about it as this functor as some kind of parallel transport functor. So it sends every interval to the parallel transport of some connection, and the requirement is that if you have a family of intervals that varies smoothly over some base manifold S, then the parallel transport which is a function of this type, also varies smoothly with respect to S. So that's something which is not true for a discrete case. Like, there is no reason why, like, well, strictly speaking, in discrete case, it's trivial anyway. So, but like such type of condition you can only get for fibered field series. Okay. So maybe now we are ready to sketch a theorem which is essentially due to Frege, but he didn't use the language of fiber categories, so his formula in more traditional terms, essentially what I just explained here, like a smooth map from path space of X to U1. But that's essentially equivalent way to put it. So a theorem by Frege says that let's see. As like isomorphism classes one smooth over X. Isomorphism classes are in bijection with isomorphism classes of line bundles with connection. Again, I suppressed some small technical details, like strictly speaking, I should be taking isomorphism classes of such manifolds E modulo some equivalence relation, but again, like that's not very important.
Is that equivalence because parallel transport doesn't actually depend on the path?
Exactly, yeah. So this equivalence in particular ensures that this functor is invariant under diffeomorphisms of intervals. That's a property that every parallel transport functor has, but a priori it's not true, but this equivalence relation in particular ensures that it's satisfied. It also ensures that on constant paths you get a trivial parallel transport. Okay, so I don't have much time left. I guess that was a very ambitious plan to explain everything in 1 hour, but I hope the essential idea of the approach is already clear, like how to do everything fibered over smooth manifolds. So maybe let me very briefly describe what the rest like. Let's see, so we can probably erase motivation. Let me first very quickly describe how you get line bundles without connection, which is part C in that outline.
See, before you go to that case, do you have an expression for the entire category of line bundles with connection?
Yes, it is possible to discard pi 0 and isomorphism classes, but yeah, I mean, you can turn this into a category, and it will be equivalent to the category of line bundles with connection. Okay, so let's very briefly describe part C. So how do you get, we now know how to get flat line bundles as topological field series. Also, we know how to write line bundles with connection as some kind of smooth topological field series. So the remaining case, which is necessary for differential cohomology, is how you get just line bundles without any connection. That is given by something called homotopy topological field series. So what is that? Well, again, like before with the same structure. So definition, if X is a space. So again, we don't need X to be a manifold because line bundles make sense on arbitrary topological space. And then a one-dimensional TFT, homotopy TFT, homotopy over X is a functor. So it's a functor from what is naturally called homotopy category of Cobordisms over X through the appropriate version of BU1. So let's describe what those are actually. Again, those are now not ordinary categories, but something slightly different. Namely, it used to be the case if you had two objects, then morphisms between those two objects form a set. But in this case, morphisms between two objects will no longer form a set, they will form a topological space. So that's again very informal, like I don't want to get into the formalism of infinity categories and so on. So I will just pretend this is true on the nose. So those two are categories enriched in topological spaces. So what is this category? Objects are well, again, points in X, so map from a point to X. Morphisms, so if you have 2 points, X and Y, in X, then morphisms should form a topological space. Well, that's a space of paths, so the space of paths from X to Y. Well, it's a topological space, so yeah. And for BU1 objects, well, there's just one object. Morphisms are U1 as a topological space. So that has a topology. Okay, so let me just very quickly state the proposition. Isomorphism classes of such homotopy field series are precisely isomorphism classes of line bundles over X. Yeah, unfortunately, I don't have time to talk about it in more detail, so let's proceed.
I've always wondered if such a thing actually exists at all.
What do you mean exist?
Well, holonomy defined on all continuous paths that composes. You're saying it does. But you're saying it probably not is non-empty.
Yes. Well, strictly speaking, like I'm not so sure about this statement without pi naught, but with pi naught it's simply can be computed using cobordism hypothesis. So this can be computed as homotopy as a space of maps from X to this infinity groupoid, which is simply a classified space of U1 as a topological abelian group. Well, by definition, there's first cohomology of X with coefficients in U1 as a topological abelian group, and that is equal to H1 of H2 of X with integer coefficients.
I guess the confusion is maybe that, so you don't require that your notion of parallel transport be compatible with composition of paths. You only require that there be a homotopy between
Yes,
parallel transport
yes.
given a path.
Exactly.
Recompose and
Exactly. So the remark is that I don't require composition, parallel transport to be compatible with composition of paths. I only require it to be compatible up to some homotopy, which is essentially encoded in the formalism of infinity categories here. Yeah. Okay, so let me finish the talk by, by first erasing another blackboard and then summarizing what we have learned so far, which takes the form of so-called character diagram. Okay, so summary. We have the following commutative diagram. So, oh, I guess I forgot to mention that such isomorphism classes are by definition called first differential cohomology of X. So that's by definition is this. So in the middle of this commutative diagram, we have first differential cohomology of X. Now we have some obvious maps. Yeah. Well, I don't really want to talk about differential cohomology of X with coefficients, but well, yeah, let's suppress this. Anyway, so so we have learned that we have those flag bundles, which are classified by first cohomology with coefficients in discrete U1. But of course, there is an obvious map here. So any flag bundle is also a bundle with connection. Similarly, we have learned that we also have all line bundles. They're also classified as first cohomology with coefficients in U1 as a topological space. And of course, there's an obvious map here, which, so to say, forgets the connection. So that's the obvious embedding. This map forgets the connection. And the composition is also obvious, like forgets that it's flat line bundle. And in fact, you can pretty much easily see all those maps on the level of field series, but I don't really have time to explain that. Now, you have some other stuff here, like, for example, this map has a kernel, namely, the kernel is the space of line bundles with connections that are trivial. So it can be identified with first differential forms of degree 1 modular differential forms of degree 1 with integer periods. So those are trivial line bundles with connection. And the last term is the co-kernel of this map, which is also known as a curvature map. If you have a line bundle with connection, you can compute its curvature, which is a differential 2 form on X with integer periods. And finally, you also have some obvious maps from cohomology with real coefficients, which is simply given by the obvious maps on coefficients here, and the obvious, like, the definition of the ramp cohomology here, and similarly here. Now, the claim is that this diagram is commutative, and furthermore, the two diagonal sequences are exact, and this one also. And a theorem, well, a particular case of a theorem proved by Simons and Sullivan.
Cheat or Simons?
You mean the uniqueness statement, or?
70s.
Ah. You mean for if n equals 1 or for arbitrary n? Like,
Arbitrary n, n
Oh.
is n.
yeah, so this diagram determines H1. So the very last statement is,
Oh, I see that. Yeah, that's the statement that we proved, yeah.
oh yeah, sorry.
Well, for n, for higher n, yeah.
Yeah.
No, but in this case, that's
Yeah, I mean,
That's what
I will right now in a second generalize this to arbitrary n. So I want this still to be true. Okay, so I described those three terms in terms of field series for U, and
we voted first.
and it turns out that this entire diagram can be generalized to the case of arbitrary dimension. So what happens is you set 1 to be equal to n and replace everything appropriately.
So now this is part 2 of the talk.
Yes, exactly.
N equals n and redo the talk.
Yeah, precisely.
Maybe there's n minus 1 or plus 1.
Yeah, the grading convention is sometimes different here by 1, yeah. Yeah. So 2 is by definition n plus 1. And the theorem, well, let's see, please. So let's finally sketch the theorem. Which essentially states that this is a diagram star for any n, the diagram star admits an interpretation in terms of topological field series of those three flavors with all definitions appropriately generalized. And in particular, it provides a description of differential cohomology for arbitrary n as some kind of appropriate generalization of the corresponding statement for n equals 1, which I explained here. I guess I'll stop here.
Questions?
I want to quibble some more about, a functor is what I think it is, right?
Here?
Functor just means a functor, right? From
Yes.
path,
No, it means it's a functor up to homotopy. So composition is not preserved on.
Where did you say that, though?
I said that when I said those are actually infinity categories. So that's
infinity categories.
yeah, that's
Okay,
informal.
okay,
That's
okay.
precise statement infinity categories.
But before with the smooth case, those were actual categories?
This
In the smooth case, that's actually, those were categories in functors.
Yes.
You only use infinity categories
In-
here.
Yeah, the infinity categories are only used in the case of homotopy field series. In the smooth case, when I say category, I mean an ordinary category, not an infinity category. So here it's, I actually said it somewhere here, yes, ordinary category. Yeah.
I mean, somewhere in the 90s, there was a work by Pavlov, who somehow also has a geometric interpretation of, say, h hat n, and maybe also of this diagram. So, have you made a comparison between this theory? I mean,
not
because it looks like also higher parallel transport and something.
Could you repeat the question?
Yeah, yes.
Gaia has an interpretation of, say, this higher differential cohomology
Mm-hmm.
in terms of.
I'm sorry, could the speaker repeat the
Yeah.
question? Then we
So-
have
Gaia is a.
Could the speaker repeat it? Then
I
we
should
have-
repeat the question, yeah. So there is a paper by Geyer, which does essentially this diagram in terms of for the algebraic geometric case, I guess, more like. No? Well, it also treats the algebraic geometric case, I think. And the question is how it can be related. Well, I don't know so far, but I plan to look into it. Yep.
Have you thought about making these objects have a topology so those things are continuous, so that, you know,
Yeah, I mean-
consistent with
They are continuous. I mean, this is in fact interpreted in those fiber terms. So it's like, I should really like smooth. Yeah, so all of those objects are interpreted in the same way as I interpreted like smooth field series.
Up there, the U1, I want to replace U1 discrete by U1 continuous.
Here?
Yeah.
Oh, but here, but this
Yeah.
diagram will not be exact.
But if that's continuous, then the kernel has a topology. It's a closed subset, so you want that topology to be coming from the natural topology that object has. If you put the circle topology.
Here?
Yeah.
But the co-kernel will be different now, or
What?
the co-kernel. So this is a like this curvature map is a co-kernel of this map. So if we allow continuous here, then we will get something much bigger, namely all line bundles. And well, it doesn't look like you can have a map like this. I mean, you're essentially, so if you replace discrete with topological, but this would amount to saying that you can equip every line bundle with connection, but that's non-canonical. Or did I understand your question correctly? Or like if you, so do I understand right that you want to say is that like topological here, or?
So you're saying the kernel of the curvature should be the flat things, so that's why you put the screen there?
Yeah, and the question maybe is what happens if you put topological here, but it's unclear to how to define a map from all line bundles to line bundles with connection in a more or less canonical way. Yes.
So I'm a little bit confused. I mean, in some of the zero-dimensional case, so where we have points, you said, okay, let's forget about the symmetric model structure because everything is free
Yes.
on the point, and okay, if you simplify, say, in the S direction, I mean, even these non-trivial coverings can be done.
Yes.
In the higher dimensional case,
Well,
is this also free?
yeah, the claim is that it's also free, and you can also get rid of Cobordisms and replace them with simply with simplices. Instead of intervals, you have simplices. Any other questions?
The board is not board anymore. So work with some
Well, we first defined it for like arbitrary Cobordisms, but then the claim is that because it's free in the appropriate sense, you can discard the monoidal structure and replace like arbitrary Cobordisms by simplices.
I think we should also emphasize that this in the form is present, if we interpret it as a statement about sort of the honest kind of Cobordism category one want to work with, this is a pre-theorem. So when we say this has a field theoretic interpretation, well, it sort of feels like one, but it's not in the formulation that we ultimately would like to have.
Yeah.
So we are using crutches to say that at this moment. It's not a finished product, it's work in progress, so it's, we should say that. Any other questions?
Just a quick question. The pi 0 is naturalized Morton classes, or what is class?
The set of, yeah, the set of,
Proposition.
yeah, the pi 0 denotes, so in which proposition? This?
Yeah, yeah.
Well, pi 0 is, well, I mean, this, this denotes actually the space of such one-dimensional TFTs. It's an infinity groupoid, which is the same thing as a space, and a space has a pi 0, which is a set of its connected components. Yeah.
What are the paths in the space?
So a path in the space would be a natural transformation in a natural transform. So the question is, what is a path in this space of field series? And the answer is, it is a natural transformation between corresponding functors interpreted in the language of infinity categories.
Any other questions? Well, let's take this speaker again. Next talk will be at